Okay, in this video now we are finally at long last going to start using GD&T. We're going to actually build up some feature control frames and use some of the concepts and symbols that we've learned so far. I am going to keep in my hand and also post on Canvas. I'm going to copy the entire chapter for tolerances of form, just knowing that some of you probably don't have a book. The bookstore obviously isn't open. I'm sure you can find them on Amazon or on the ASME website, but nevertheless, a lot of this is fairly simple, and it's easy enough for me to copy pages of the standard for you to have in your hand. The reason I'm going to do that is I'm going to teach right out of the standard. I'm going to use the illustrations that are in the standard, again, for two reasons. One is that for as thick as the terminology is and as impenetrable as some of the writing and the terms in here, the illustrations are very good. I will say that they did an excellent job giving practical examples of the different aspects of GD&T. And what I really like about it is they'll show an example of a feature control frame, and then just below it they'll have a series of illustrations that actually are stated, says means this. And they explain, I think, fairly clearly what that feature control frame is intended to do. Now, this isn't something you can just browse or glance at. You have to actually spend a little time reading it and thinking about the geometric aspects of the requirement. The geometry isn't a natural way of thinking. We have already some unnatural concepts of lines, points, and planes. It's just not the way we normally think. But if you read these illustrations and nothing else, you'll come away with a fairly good understanding of how GD&T works. The one thing I don't like about the illustrations is, even though there is an English version of the standard and a metric version of the standard, it's pretty clear that the illustrations and the dimensions and tolerancing that they use are intended to be metric. They don't say that, but again, when you look at the size of the tolerances and the size of the features, it's pretty much drawn in millimeter units. The units really don't matter too much to us. We can think about the dimensions in millimeters or in inches. It really doesn't matter. Obviously one's bigger than the other, but the same concept applies. A limit is a limit, a tolerance is a tolerance, and the feature control frame is going to put a tolerance zone up that will be some number, and that number can be a metric number or an English number. So let's go ahead and start right out. Now again, I'm going to keep this standard in my hand here so I can refer to the illustrations, and then you'll be able to follow along with a paper copy of the same illustrations. We still have a few unusual concepts to get through, but I'm going to start out with probably one of the simplest and most straightforward controls that we have in the toolbox. This is one of the tolerances of form, and this is for straightness. Now, if you remember when we talked about points, lines, and planes, we said that we're using these perfect geometric entities to use as a basis of comparison to an actual feature. And we'll say that, when we say something is straight, we want to think about how straight is it? Well, what is the most straight thing in the world? Well, the most straight thing in the world is a geometric line. So we are using the geometric line as a basis for perfectness and as a point of comparison to say, I would love my features to be perfectly straight, but they can't be. I am simply going to measure how not straight they are and how much they diverge from a geometric line. Now, I told you that we can't create a perfectly straight or a perfectly flat or a perfect anything, but we have established enough mechanical accuracy that we can get something very, very close to it. For instance, a laser shoots a line that's pretty darn straight, and it's a good comparison point. And even though we might be talking about errors in a millionth of an inch or so, doesn't matter. It's way beyond what our immediate needs are. So, let's think about in the back of your mind that all of these controls are ultimately going to rely on a perfect entity of some sort, in this case, the geometric line. Okay, so if you've got your handouts off of Canvas here, we're going to be actually working in, I think it's chapter 5 of the standard, and I'm going to start out with the very first illustration in chapter 5, which is specifying straightness of surface elements. Okay, I'm going to draw up the illustration. At this point, you all recognize what this is, right? This is a feature control frame. It is going to tell us what we are controlling here, and it is going to tell us what the size and the nature, everything about the tolerance zone that we're going to need to know. So, as a refresher, this is the control symbol. In this case, it is straightness. And here we are going to put all the tolerance zone information that we need. Unfortunately, we don't need much. So in the illustration, you're going to see that. Now again, just as sort of a giveaway in the metric world, if there is a 0 in front of or to the left of a decimal point, they put it there. In English usage, inch usage, we don't normally do that, but I'll just put it back here so it looks correct. And I'm missing one piece of information here. Okay, some more giveaways in terms of the metric nature of these illustrations. This is obviously a limit form. They've already put the dimension in limit form for us, which is kind of nice. In metric notation or metric usage on drawings, they skip the little bar there. And here's the true giveaway, and that this isn't going to affect us at all. This is actually a notation of a group of tolerances, standardized tolerances. It has nothing to do with the GD&T. It is simply a notation that says that the tolerance implied by these limits is a standard tolerance. So we'll just take that off. That's not going to impact us at all. And now here we are in GD&T land. We have already established a tolerance zone. Now we just need to determine what the nature of that tolerance zone is. And you're going to hear that term from me a lot. In order to understand GD&T, you have to be able to express in words what the nature of the tolerance zone is. And I'll be asking you frequently, or I would be if you were in the classroom, I will be stating on the video what is the nature of the tolerance zone. We are going to try to draw, just like we drew in an earlier video, we drew the square tolerance zone that we really didn't like. We still want to be able to visualize and draw the tolerance zone that the feature control frame is giving to us. All right, so let's let that sink in a little bit here and visit a concept now that is also sort of unique to GD&T. It's not something we think about a lot, but it becomes very important as we go along here in GD&T. You'll notice on the illustration that it says specifying straightness of surface elements. Okay, so if they take the trouble to make a distinction between surface elements, we have to ask, well, what other sorts of elements are there? We'll get to that. But an important distinction that GD&T makes, and is not a natural way of thinking of features, is that we can control a number of different elements, even on something as simple as this, call it 16-inch round bar. Unfortunately, the standard doesn't do a super good job of making that distinction really clear. They sort of bury this concept in how the notation is put on the drawing. I really don't like that. But I'm going to point out to you how they want you to interpret these things, and so that you can make that distinction. It is a critical distinction. It makes a huge difference in how you interpret a GD&T callout. Okay, so in the case of surface elements, we are going to state that when the feature control frame is touching a surface, when it is drawn either with an arrow pointing to the surface or to an extension of the line or something like that, where it's obvious that we are dealing with the surface of that part, we are controlling surface elements. Now, let's think about what that really means. This is a cylinder, 16 inches in diameter, some length. They don't give you that because it isn't important to us. The surface elements are geometric entities. And since this is a straightness call out, we know that we are going to be controlling some sort of linear element. Straightness is a comparison to a geometric line. Well, where is there a geometric line, a straight geometric line on this curved cylinder? Well, everywhere. If you take this cylinder and just as it's drawn, if you were to run an indicator along that edge, right exactly at the 12 o'clock position, you would see that that is a geometric line. The touch point at 12 o'clock is a geometric line if the bar is straight. Is that the only geometric line on the cylinder? Well, no, obviously not. There's one at 3 o'clock, there's one at 6 o'clock, there's one at 9 o'clock, and every other position around that cylinder. So there are geometric lines all the way around that cylinder. Like all geometry, we think in terms of infinite. Obviously, a geometric line has length, but it has no diameter, so there is an infinity of lines. We can take a million, gabillion readings simply by rotating that bar and checking the straightness of those linear elements. This is what the feature control frame is telling us, is we are concerned about how straight the surface of this bar is. Now you say, well, which line, which one of the infinity of lines are we concerned about? And we're concerned about all of them. But we have to make a decision. We have to decide, if I check one at every clock point, say 12, is that enough? How about only 4? Maybe I just need 4. You need to decide that. The standard doesn't tell you how many of these you have to check. You have to check enough to make sure that all the surface elements are straight within the tolerance zone. Okay, so with this surface element concept, we're going to compare that to the only other line really that would be of concern to us would be this line. That center line. Is that center line a geometric line? Well, if the bar is straight, it is. But it is different. It is certainly different than the surface elements, all the lines that make up the surface, in that, for one, the line is buried in the bar. We can't really touch it. Does it physically exist? Yes, there's material in there somewhere that if we could extract it out, we could measure it. But not an easy thing. Let's look at another scenario where we would have a tube. In this instance, we also have a center line of that tube, just like we have a center line of this bar. Does that center line exist? Well, no, it doesn't. It's nothing but air there. It's a little bit easier to get in there and check something, but there's nothing to check. That concept and the distinction between a surface element and these types of linear elements is that we have a concept of surface elements, and the other type of element, which the standard clumsily defines as a derived median element. So, even at this simple level, we're going to run into concepts that aren't obvious, aren't artfully defined or given easy terms, but we have to make a distinction between a surface element and a derived median element. One, because the surface elements physically exist, they can be checked in a certain way with certain instruments. The derived median elements, usually not. Usually we can't put our fingers on them, or they don't exist at all. They're simply a concept. And in the case of a derived median element, we're usually talking about just one element. In the case of surface elements, we're talking about usually an infinity of them. So the distinction is clear. Theoretically, the distinction in GD&T isn't always clear. What I want you to remember now, and I'll explain later about the derived median element, but for right now, if the feature control frame is pointing or touching a surface, we are controlling the derived median elements. Now there's going to be another clue when we get to derived median elements in the feature control frame that we are talking about a derived median element, but it isn't always, that clue isn't always there. Alright, so let's get rid of this for the time being. We're not going to talk about derived median elements. Now we need, since we have all the elements of a geometric specification, we have a feature control frame, we have a control symbol of straightness, and we have a tolerance zone. Now we step back, make the determination that we are talking about a surface element that we are going to control. How many? That's up to us. And the question we're going to ask ourselves, and I'm going to ask you frequently, is what is the nature of that tolerance zone? Remember, the tolerance zone in the earlier video was a square. We didn't realize it. We didn't think about the consequences of the square corners. But we always have to think about the nature of the tolerance zone in terms of what its size and what its nature is. And in this case, it's fortunately pretty simple. We know that we are going to control a linear element. We know that it has a zone size of 20 thousandths. Let's say that's 0.02 millimeters, I'm sure, but I'm going to call it 20 thousandths. Now we just have to decide where do we locate it and how do we distribute it around the actual feature. And that's pretty simple. We locate it. We locate it around the feature that we're trying to control. In this case, we are focusing strictly on the line at 12 o'clock at the top of this bar. The tolerance zone is 20 thousandths wide. The tolerance zone consists of two parallel lines, one 10 thousandths above the surface, one 10 thousandths below. In the standard, they call that equally disposed. Now again, that's another one of those terms that we wouldn't normally say it that way. We would say equally distributed, but equally disposed means that it is split. Half up and half down. So half the tolerance zone is above the feature as drawn, half of it is below. We're going to be able to change that later, but the assumption, or not the assumption, the default position is always equally disposed. So whenever we put any sort of tolerance zone up, no matter what its nature is, unless otherwise specified, it is equally distributed about the feature. Now what is the feature? It is this perfect straight line as drawn. There's another thing that is expressed but not frequently enough, I think, in GD&T is what is the range of the tolerance zone? We know how wide it is, we know what the spacing of those two lines are, or what the spacing is, but how far does it extend? Well, it extends as far as the feature does. So the tolerance zone starts here and ends here. It starts where the feature starts, it ends where the feature ends. We're going to be able to change that too, but again, the default position is the tolerance zone is as long as the feature is. It's equally spaced, and the spacing is as specified in the feature control frame. So you can think about that like a fence line, or spray painting a boundary line, and that means that we now have some obvious limits within which we can evaluate the straightness of that element. Once we've done that, and this is something you must never forget, once you have defined a tolerance for that feature, anything goes within that range. Even though the drawing shows this as a nice straight element, in reality, since we have 20 thousandths of running room, plus or minus 10 thousandths, anything can go on in that boundary. And we have to accept that as an acceptably straight part. So if this surface, instead of being straight as it's drawn, actually looks like this, and we end up with a part that looks like sort of a barrel shape, as far as the straightness is concerned, these surface elements are straight enough. Now again, this is intended to be a metric specification that is a much, much smaller specification than 20 thousandths of an inch. So this is in inches, this would be a pretty big tolerance for straightness. But the same thing applies. Once those boundaries are established by the feature control frame, you have no basis for complaint. That surface, that linear element, can do anything that will fit in that boundary. And this is something that engineers are supposed to think about. They're supposed to think about if something goes wrong or if somebody goes nuts, what could really happen inside those boundaries? Well, in this case, a lot could happen. I could end up with something like this. So I'd have a surface element that looks like this. I could have a surface element that looks like that. Looks like a rutted road. So, whenever you apply these, whenever you interpret them, you have to bear that in mind, is that the tolerance zone, once it's established, is a free fire zone. That anything that fits is acceptable. And you can run into some pretty weird scenarios if you're not careful. One thing I will say about all the form controls is the form controls are intended to be sort of a limit on how bad these things can get. We want to make sure that we control the form of things well enough that we can measure adequately other aspects of the features. So these tolerances tend to be relatively small. Straightness, flatness, those sorts of controls of form are usually intended to give us a good basis, a good starting point for other measurements. Okay, so now let's think about that though. Does this mean that this line, even if it were perfectly straight, that it can be up here or down here? In other words, does this adjust the size of the part? And it does not. The size limits are already specified. The size limits of 16 and 15.89 must never be violated. That is a key rule in GD&T. So let's say you end up making one of these shafts and it is right at 16 on the diameter, 16 inches in diameter, and we still have the 20 thousandths feature control frame. Does that mean that you get another 10 thousandths above it for this surface to go nuts? It does not. You can never violate the boundary of size. So no matter what this tells you, at no point, no matter where you measure, we can't end up with something like this where there'd be a location on the shaft that would violate that 16 inches of diameter. So that effectively throws that tolerance zone downward So the 20 thousandths tolerance zone is shifted all downward, and all the tolerance variation would go inward. Again, as long as we don't violate upward and inward too. So the limits of size are considered inviolate. You can never violate size